Okay, with this lesson we get into calculus proper. I mentioned at the beginning of the course that almost all of mathematics relies on functions, and then once you start the idea of limits, you are in the realm of calculus. That's what we're going to be starting today, and then we use limits to talk about both finding the slope of a curve and finding the area underneath a curve. And those two things are connected by the fundamental theorem of calculus. And so we've just done this. Now we're going to start this. And let's begin by talking about this particular function. And like we've said before, I want to know what that function looks like, want to have a sense of its behavior and such. And so you can throw different values in, and you can put in, let's just put in some values. Here's x, and here's y is equal to f of x. And so you put in 0, and you get what? 3, it looks like. 9 over negative 3 is 3. Put in 1. You're going to get 1 minus 9. Let's see, what's f of 1? F of 1 is going to be 1 minus 9 is negative 8. And 1 minus 3 is negative 2. So negative 8 over negative 2 is 4. And you put in 2. And you're going to get what? F of 2 happens to be equal to what? 2 squared is 4. 4 minus 9 is negative 5. And 2 minus 3 is a negative 1. So that's going to give you 5. Okay, then you put in 3, and you're going to get 9 minus 9 on top, which is 0, and then you're going to get 3 minus 3, which is 0 on the bottom. Whoa, remember what we've said, when you divide by 0, you don't get anything. It's undefined, it makes no sense. So there's no value of the function here, okay? Just put a big box there with an x through it. There's no value of the function at 3. And we could go on and find values of other things as well, 4, 5, negative 1 and such. Well, that's all fine. But even though the function isn't defined at 3, it would still be kind of nice to know what's the behavior of the function around 3. What's happening to the function, at least as you get close to 3. Basically, what do the neighbors look like? So let's see if we can figure that out. And I think we can, because if we factor the top, notice that this numerator factors into x plus 3 times x minus 3. That factors as such. And the denominator, of course, is still x minus 3. And then we can divide this out with this. For any value except for 3, this number is going to be exactly the same as this number. Agreed? If I stick a 4 in here, or a 15, or a 3.1, or 3.005, whatever number this is exactly the same. So this number divided by this number is going to give us a 1. So it's not going to affect the rest of the function at all. This thing will always give us a 1, so it won't affect the behavior of this function. However, it does affect it just at the value 3. Because at 3 there's nothing that comes out of the function. So now I have an idea what this function looks like. I know it's going to look just like the function x plus 3. If I want to, I can even write this is equal to x plus 3 as long as x is not equal to 3. Okay? At 3, it's undefined. But except for that, it's just the function x plus 3, and that's a line. It's a line with a y-intercept of 3 and with slope 1. So it looks something like that. That's what this function looks like, except, as I just said, at the value 3, this function doesn't give us anything. So what you have to do is you have to make a little hole right in the function right there to indicate that this function here looks just like this, but at the value 3, nothing comes out. So that's what the function looks like. So now that we know what the function looks like, is there any way that we can express the fact that as x gets closer and closer to 3, the value of the function is going to be getting obviously closer and closer to 6, because anything except 3 is just going to be this. So as this gets closer and closer and closer to 3, the value of the function is going to be getting closer and closer and closer to 6. The problem is we can't say that f of 3 is equal to 6. We can't say that. It's not true. But we still want some way of indicating the fact that as you get closer and closer and closer to 3, this is getting closer and closer and closer to 6. It's the next best thing to this. And so that's why we come up with a new expression in mathematics, and it's the expression that's written like this. It's the limit of the function as x approaches 3 is equal to 6. So it's not true that f of 3 is equal to 6. There is a hole in the graph there, but it is the case that as you get closer and closer to 3, coming in from both directions, the value of the function is getting closer and closer to 6. Another way of thinking about it is, no matter how small of a little interval I want to put around 6, I can get everything within that little interval by choosing something close enough around 3. All of this stuff will get sent in there. If I make this little interval even smaller, then this will become even smaller, and that can get sent inside, with the exception of 3 itself. With 3 itself, we don't care what happens. It's just as you get closer and closer to 3, the values of the function are going to get closer and closer to 6. So that's the notation that we use to express this idea. So then you say, well, okay, fine and dandy. That's all great, but where would you ever use that? Is that just something to take up space, or is there any real use for it? Well, let me show you why there's use for it. First of all, I'm going to have to get rid of this picture now, just for sake of space. But hold on to this thought that the limit of our function as x approaches 3 is equal to 6, okay? So remember that. Now, let's go back to what I said in the very first lesson when we introduced calculus. We were asking the question, suppose you have a parabola, it's not a bad looking parabola, and you're at the point 3 right there. You can think of driving down a road, where you're driving down the road like this in a car, and you happen to be at this point right here. So I guess that's the point, what, 3, 9? Since this is a parabola, let me write down the equation over here. Y is equal to x squared. There's the parabola. So you're at the point 3, 9, and you're driving down the road, and you're interested, what's the line, the slope of the line that your headlights would be shining on if your car were right there and they were shining straight ahead. Or another way of thinking about it is, if you were to put a straight edge right up against this curve at that point so that it touches it just at that point without going through, but just touches it, the word is tangent to it at just that point, and then you were to ask, what is the slope of the line that you get from this straight edge right here, then what would that slope be? Okay, if you were to talk about the slope of a graph at a point, that's what we mean by the slope of the graph. We mean if you were to put a straight edge right up against it, what would be the slope of that straight edge, of that straight line? So that's what we mean by slope, and we're very often interested in what the slope is, but how do we go about getting it? And here's how we go about getting it. We say, well, let's choose a point just a little bit away from 3. Let's choose 4. That's convenient. So there's the point 416 right there. And then, instead of finding the tangent line here, which we don't know how to do yet, let's just find the secant line that goes through those 2 points. Secant means it hits the graph in 2 places. And we can find the slope of the secant line easily enough. What is it? It's going to be 16 minus 9 divided by 4 minus 3, which is 7. So the slope of the secant line is 7. And just by looking at it, you can see that that at least is going to be in the rough ballpark of the kind of slope that we're looking for at that tangent line. How can we get a better approximation for the slope of this tangent line? Well, hopefully you said, if you're thinking about this as we go, let's choose a point a little bit closer to 3. Let's choose 3.5. Let's do the same thing here. So if we take 3.5 and then 3.5 squared, and I don't have all of these all figured out right here in front of me, but you can do it on your own if you like. And then we find the slope of what happens if you take 3.5 squared minus 9 all over 3.5 minus 3. I know what the answer is. By the time you get done with all that, you end up with 6.5 as the slope of this line, slope of that secant line. Well, that's better. But why stop there? Let's just, how about choosing 3.1? Okay, how about choosing that point right there? So what's the slope of that line going to be? It's going to be 3.1 squared minus 9. That's the change in the y values. Here's the change in the y values. Divided by 3.1 minus 3, which is the change in the x values. And again, I know what the final answer is, that you end up with 6.1 for an answer, or something very close. So that's all good, but what you see, what we're really doing is we're saying what happens as you let this value here get closer and closer and closer to 3. So what we're really interested in is if you take, let me change this now and just call it the point xx squared. Here's xx squared right there. What we're really interested in is what happens if I take the slope of this secant line right here, which is going to be x squared minus 9, there's the change in the y values, over the change in the x values is going to be x minus 3. There's x minus 3 right there. And what do I want? I want this as x just pushes all the way into 3 as it gets closer and closer and closer to 3. Ah, I want the limit of that as x approaches 3. That's exactly what I'm after. And notice, that's exactly what we discovered right here. I'll do it one more time. Is equal to the limit as x approaches 3. You can factor the top over the bottom. And now all you're interested in now is what happens as x approaches 3. So as x approaches 3, these will always be the same value, so the ratio will be 1. So as x approaches 3, this thing will get closer and closer to 3. This stays 3. As this gets closer and closer to 3 and you add it to 3, this whole limit is going to get closer and closer to 6. Aha! There's what we wanted. We just found the slope at this of the tangent line. That's what we were after. We found the slope of the tangent line because we actually pushed the x all the way into 3. We took the limit. And that's exactly why limits are important. And so in the next lesson, we're going to talk about limits more generally. And then once we talk about limits more generally, we're going to come back and use limits for this idea a lot, because this is why we're interested in limits in the first place, is to be able to find slopes of tangent lines.